Okay, now we talk about domain. Domain, okay. Domain. Okay, so what is domain? It says that if y equals to fx is a function, the keyword is a function, then set x is the domain of function y, x, y. Okay, let us look at this statement carefully. If y equals to fx is a function, okay, then set x, x is the element, set x is a domain of a function. So we understand that domain because of y of f is denoted as y a d small f here, and it is a set 集合. And this set, the element is x. So x can be anything, okay, then blah blah. So this is a function, we call it a domain, okay. So there are three definitions here. A domain fx must be stated when defining a function. When you define a function, just like a physics, you learn definition, define. I use another kind of pen. Define a function. I like to use this. Define a function. First, you have to state the domain. First rule. Second rule, a function only fully defined if domain is specified. The domain must be specified. Domain normally is easy to get. The domain of a function is not specified, then it is usually assumed that the domain of the function is largest possible value. If not specified, if it is not specified, it is assumed that so now A level you have a lot of theory, you have a lot of concept that you need to understand, so bear with it. If it's not specified, it is assumes that the domain of the function is the largest possible. So there is a keyword here, largest possible domain of which function is defined. Of which function is defined. So it's the largest possible domain of which function is defined. So let's go through some example. Example number 1. If you have fx equals to x squared, so what would be the domain like? You see, this is x squared. We know that x squared is always bigger than 0, but x can be any number. It can be minus 1, 1, minus pi, pi, minus 3, square root 3, right? So there's nothing that we can, x is constraint, so that the domain of f is equals to r. R is a real number. So now I need to recap the things. Real number, positive number is z, integer is z, and natural number start from 1. Okay, natural number is only 1, 2, 3, 4, 5, but this z, it can be z plus, z minus. That means that positive integer, negative integer. Positive integer essentially is real number, and you can be whole number which have 0. Okay, starting from this whole number here. Okay, 0 minus 1 minus 2 minus 3 equal j. Alright, so you could have a lot of number. Then later on we'll look about complex number C, okay, and imaginary number. So that will come later. It's not so fast. Let's go to another example. Okay, fx equals to square root x. So we know that whatever in the even number root, x has to be bigger or equals to 0. So the domains of f is equals to 0 to infinity. You can put in this manner, or you can write as, okay, x for x bigger to equals to 0, x is r. Okay, so this is a two way of writing this thing. Okay, got it? I repeat again, is x for x bigger or equals 0, x belongs to r. This is how we write it in mathematical language, or in simplicity, I prefer that you write in that manner. Okay, the one I circle. Well, we look at the third example. Fz equals to minus 1 plus z. Okay, z is complex number. So complex number, we are not going to touch on this thing. So that z itself, it can be the fx itself can be a complex range, imaginary range. We are not going to touch on this at the moment. Okay, so we have already finished domain. Now we talk about range. Range. So range is defined as if y equals to fx. F is a function. Element y is the image of x. You see the definition is under f. So f map x to y, mapping. So the range, we call it co-domain, but normally we use the word range. It's easier to understand. Of f is the set of the image or images. This is more difficult to find. Okay, so normally, how do we denote f range? We use RF to denote range. It's a set. Again, it's a set. Y is an element, and this is a set. Okay, so now the range of f functions can be sketched by a graph. For example, like this. You have this is a g function mapping across. So 1, 2, 3, 4, this 5, 6, 7. So you look at the range here. Normally 2 map to 5, 3 map to 7, and 4 map to 3. So the range of this is 3, 5, 7. Okay, this is a simple illustration. Okay, but domain of here is 1, 2, 3, 4. Range of G, not F, G is 3, 5, 7. So this is how we define range and domain. However, the life is not so simple. So we look at this example. Y, and this is gx, x. So you look at this in the graph, you look at this, the x value itself across 0, it can be the domain of g, it can be from minus infinity to infinity. But the range of g, you look at this, is never cross below x. So it can be from 0 inclusive to infinity positive. Okay, so this is the range of x, or you can denote as x, y. Okay, for y bigger or equal to 0, y belongs to R. That is how we denote the range. Okay, on here you can just write belongs to real number with the R with a stroke here. It means that it is a capital R. Okay, don't confuse this R and this R, different R. Okay, this is real number. This is range. Understand? Okay, let's look at one example how to find range. Okay, there's another one that they want to me talk about. This thing is called discontinuous function. What I mean discontinuous function? That means the function is not continuous. What do you mean continuous? Continuous means that you see, you draw a line, it will never end. You see, you will not stop. Yeah, your x can be, but once you stop, for example, right now I stop at this is -1, there's nothing here, and this is nothing here, 2 nothing here, 3 nothing here. It's called discontinuous function, or it's called discontinuous function, or there's something like that. Y and x, I have, when x equals to 1, it give me this value, probably 1. If y equals bigger than 1, it give me y equals to 2. Okay, the yellow one, the blue one belongs to not having, and the 2 is here. So this discontinuous at 1, because 1 itself, it can be 2 and 1, you see. But -1, you know that it becomes to 2, so it's 2. But when you less than -1 a little bit, you become 1. It's called discontinuous function. Okay. So let's look at one example. F for x mapping up from absolute value x when x is more than 1 is 1 when for x -1 and 1, and for 2x plus 1 when x is bigger than 1. Okay, let's draw this thing. You know that when x less than 1, less than -1 is here. So this is absolute value of x when y equals to value of x. So which means that this is 1, y will be 1. Am I right? So when it's 2, y will be 2. Correct? Less than minus 1. So it is something like that. And dot here. Correct? You just plot it lah. Then when this is less than 1, which means that this point is not included. When this is equals to minus 1 and 1, this gives you 1. So 1, so this is included with this. Okay, I use a blue pen. But this is not included in this one. So when this is bigger than 1, I use a yellow pen or pink color pen. This will be 2x squared plus 1. That means that 1 become 3. Correct? And 2 22 42 8加9是9, something like that. So you see that it is a discontinuous function. From here, it's probably continuous because it's approach to 1, but from here it's discontinuous. It's called discontinuous. But when you learn about this discontinuity in university, you know that, the fundamental calculus, it will tell you what's the definition of limits. Okay? Then you learn about discontinuity. Okay? So we stop here for a while.